Here you go.
Yeah.
Okay, hi everyone. Let me present zkCloudWorker. When we started with Mario discuss our project in January of this year, we were inspired by the challenge to make user interface really fast. Because what we've seen on many zkApps is that people need to wait like 3 minutes for compiling, for proving, and only then they able to send the transaction. And we wanted to make it much faster. So let's see an example how it's working right now and what basically we can do. It's example of UI interface. Let me enter some number here and send zkApp transaction to the network. I'm pressing sign as the transaction is being prepared, and immediately I'm receiving signature request for zkApp. I can sign it, and it's basically just 1 second. And then in the background, we're sending to zkCloudWorker information about this proof that need to be compiled, need to be prepared. Then we fetch, as soon as it will be ready, information about transaction, send to the network. So it's not going in the browser now. It's going in zkCloudWorker, in the cloud. And on the browser, you don't need to compile. You don't need to prove. You don't need to do anything. Just yes. So it's we got the result, and we got transaction ID. So we can open Mina scan and see the transaction that yes, we set value 10. So why it's important? It's important because you can actually have 1 second delay between after the user press the button. In 1 second, you're able to present signature request for zkApp transaction. And all the complexity of compiling, proving, sending to network is hidden from the user. So you got very nice user interface, and you can also use now zkApps on, for example, low-level PCs on mobile devices, and so on, because you move this burden of compiling and proving to zkCloudWorker. So what zkCloudWorker is? It contains from the several parts. It's AWS cloud, where there are some workers. It's library that you need to import and use to use it. It's command line interface tool used to deploy the repo to the cloud, and some examples that you can use. So let's look how it's working. In your repo, you need to define some zk program, some smart program that you will use. Then you define the code of the worker. In the code of the worker, you need to basically define the code that compiles your zk program and smart contract, that creates the proof, that merges the proof to calculate recursive proof, execute various tasks you want to be executed, verify proof, for example, or send transaction. And then you define just one function called zkCloudWorker that provides this class on our cloud infrastructure. Then basically to use it, you need to set a version of your app when you want to deploy it. And then you will need to use command line interface tool that deploys. So command line interface tool called, of course, zkCloudWorker. The main command is just deploy. So you can say zkCloudWorker deploy. And now this wrapper is being sent to the cloud. What's going on in the process? First, the repo is being zipped, then it's being sent to AWS, copied to EFS data system that we created. We install yarn or other package manager that is required, install all dependencies in the process, compile your repo, and create repo record that you can use later when you actually are doing it. And if you have some old deployments, we remove those old deployments. Okay, so deployment is completed. It took 45 seconds. Now we can test it. You can use it on many chains. So let's basically choose DevNet right now. So we're saying yarn DevNet run. To run now, it's on the Mina DevNet. And we see all the logs. So we see that we're running now the worker that we just deployed to the cloud. And it's now preparing first transaction. It's getting some deployer from our cloud service that you can use for testing with some balance. So you don't need to provide your private keys for testing. And we have some pool of those private keys that rotating and allows you to send transactions. That your zk program and smart contract is being compiled, and they compiling using prover keys that already cached in the cloud, and they store it on AFS. So the compiling is faster because of the usage of those prover keys. Then you create a transaction. Right now it's creating smart contract transaction. And the transaction is being sent now to the cloud. So then it's deployer is being released, and we see that basically there is some transaction hash of transaction that was just created. So let's go to see this transaction right now. Yes. Let's wait. It's just fresh. So Mina can't probably yes. So yes, memo one, it's our first transaction that we actually sending for this contract. And the next transaction will calculate recursive proofs. So now the recursive proofs of 3 transactions is being calculated. So first we will see how 3 proofs are being created, and then they are merged. And for it to work, we will use this worker and the functions that called create and merge that handle all this stuff. So basically, you need to use 2 APIs. First API is that is being used on the cloud. For example, you get deployers or something else. And the second API, it's client API, when you call your worker in the cloud and you use it on your user interface on the web. Also, there is local testing class that allow you to test it on all blockchain. So for example, as you see this example, you can use on local blockchain, on Lightnet, on zk, and on DevNet. On AWS, we have dedicated workers, one pool for Mina DevNet, one pool for zk DevNet. We have recursive proofs calculation and verification. We have preparing, proving, and sending transactions that is working. Tasks, because you need probably to monitor some send transaction and send next after that. And some storage for repo and provers key cache. And we also developed several examples. So you just seen general example. I also did you demo of sending transaction from the web without compiling and proving. And let's now look at encryption example. Let me stop sharing my screen and give.
I am here. Okay.
You're back. Yeah.
Okay, Mario.
Okay. I will share my screen now, and I will show you the okay. So finish. Yes. I will show you the encryption example. The problem we have with the workers when we deploy them as Lambda functions on AWS is that you start the worker and you have to wait to wait till it finishes. The worker cannot interact with any other with any other thing when he's running. He starts and he ends, and so we need for the encryption example or for the encryption in general, we need to send some information to the worker. So what we have done here is just to use message MQ, which is called nuts.io, which is quite fast. And what we are doing here is just that the app, when it starts running, it connects to the nutsmq message queue and subscribes with his public key. And then he sends the public key to the worker when he starts the worker. The worker then responds and replies, does a request to the app by sending his worker public key and using the subscription where the caller has already subscribed. So that's the way that we can get the app and the zkCloudWorker connected and sending bidirectional messages between them. So the worker then sends a request for the options, for example, environment, encryption options, etc. And the caller replies with the options encrypted using the worker public key. Because the worker has only while he's running his private and public key, the worker can decrypt the message. When the worker is ready to execute the payload, he sends a message to the app requesting the payload, which is again sent encrypted to the worker, and the worker does its job, and when it's done, it sends again a message to the app indicating that it has finished. This is quite useful because it allows encryption to be done point to point between the app and the worker without any other intervention. I have here I can show you the code a little later, but here I have an example. We can run it. And you can see here that first it defines the client address and it sends. Then here the client receives the option from the worker. He sends the encrypted options. He already receives the ready message, and he sells he sends the encrypted payload to the worker, and the worker is now executing. And when the worker is done, it sends, still running. It will return the result of the worker, also encrypted, but encrypted with the client public key. So this handshake between the caller and the worker is always encrypted. Here we receive the done message from the worker. Just wait a few seconds more. And then we get all the encrypted information, and we can decrypt everything. Okay, so this is how encryption works between caller and worker. There's also other small example that we prepared, which uses the social cap deposits. And well, it's just a standard worker. We can run it, but I don't know if we have enough time for it. And we have also prepared, let me see if I can find it. Yes, how it will work in a web app. For example, we are using it in social cap to provide the payments for the claims. And you can see here, we can go ahead. We have all the wallet already connected. We confirm here. And then you can see here in the log that it is running the job in the zkCloudWorker. You see here. So in one case, we have an encryption handshake between client and worker, and in this case, we are running the worker from the web app with quite good improvements in the UX. I will show this later on the social cap demo. But you see here, we have all the log. And it's almost finished. It takes around 20 seconds. It is doing a payment and registering some things. And then another important thing is that the worker is not sending the transaction, but we are receiving the serialized transaction that we can later confirm with the wallet, and then it will send the full transaction, and we have the transaction here, and it's done. So in this case, the caller sends all the work to the worker, but we don't send any private keys because we don't need to sign the transaction in the worker. The worker is just creating the transaction, proving it, and sending the serialized transaction back. Then we use the wallet in the app and sign the transaction there, and the wallet finally sends the signed transaction to Mina, to Mina. So in this way, we don't have the problem of sending the private key to sign to the worker. Okay. So that's everything in my side. I will stop sharing. And I don't know if Michael has something to say about this.
Yes, let me finish my presentation on integration. So we integrated with zkNetwork, and it's quite fast. So transactions are almost immediately accepted to the chain, and it takes usually something like 1 second. It's fully supported by zkCloudWorker. It's integrated in library. And we have dedicated workers for Zk on the cloud. So when you send the job to our cloud saying that it's for Zk, dedicated workers are being used for zk, and you just O1JS library and zk scan explorers you usually do with Mina.net. Then we have 3 integrations as of now. One integration is with Mina domain name service, the second integration with social cap, and the third integration with Mina NFT. Those 3 integrations are already exist. And the model architecture allows for fast integrations with any project. You can just take our example and integrate with zkCloudWorker in maybe 1 hour, just taking the example. Okay, thank you. So it's all the, regarding the presentation, and we're ready to answer any questions.
Thanks. Thank you both. I already see a question in the chat from Matej.
Okay, actually, when we saying about HTTPS encryption, it's an encryption between the web browser and our AWS endpoint. And what Mario was explaining is encryption between the code in the browser that of the zkApps program and the worker in the cloud. So here we bypass AWS layer where we handle this data. So this data is not actually, it's hidden for zkCloudWorker. We're not able to process it. We just call the worker in the cloud. It's getting and decrypted directly. And it's one of the reasons why it's better than simply using HTTPS. Mario, maybe you can add something to it.
Yes, another one thing is that if you are using HTTPS, the information you're sending to the worker it goes through all the AWS message passing till it gets from the endpoint to your worker. So there are a lot of things happening between the API call, or when the API call is received in the endpoint or processing the endpoint, to the worker starting to do its job. So that information can be trapped by, in fact, it's trapped and can be trapped by AWS. So I think it's an additional level of encryption. That's one of the things. The other thing is that by using this message passing, this message queue between the worker and the caller, we have the opportunity, which is not easy to do in Lambda functions, to have a bidirectional interaction between caller and worker, and that's an additional thing. But that interaction, to be fully protected, we think that this level of additional encryption is good, because things will go through the message queue too. So there's another attack point there in the message queue that this additional level of encryption can protect. Of course, experience will tell us. We have to work and we run things till we get more information. So,
yeah. There was a follow-up question, but I guess you addressed it, or
I think that Mikhail can answer the second question better than me, but I think we have some additional levels of protection for the worker code.
Yes, basically the worker code is located on EFS, and we are now working on using the tools so it will be protected from other workers and maybe encrypted. We're now thinking how to design it better. In theory, yes, because you send to us the code, we theoretically have the possibility to change it. Practically, we try to isolate it as much as possible in the cloud environment. And in the future, not during zk cohort 3, but maybe on the roadmap, we plan to use security enclaves that will calculate those proofs, and there you can control fully basically what's going on. It's on our roadmap, and we're thinking now how to implement it. We need several features from O1.js. We discussed it with Gregor already, including having full witness and so on. So as soon as it will be available in O1.js, we can try to implement the next level of protection, but not in the next 2 months. It's maybe end of the year, more reasonable.
Yes, and I would say that also we are, some people ask in the previous work, we are also thinking about the ability to deploy in just your own host, the workers in your own host, and have a full worker environment that can run in your self-hosted environment, and then you will be but of course that's a problem that you have to deal with the security of your environment too, and AWS does that quite well. But we are also thinking about that. We have planned architecture for that too, but not in this phase of cohort 3.
Yes, on AWS there are tools that allow to do it. For example, in KMS keys, we can generate keys for the user that we don't have access to. And therefore, we're not able to decrypt the data of the users, although this data is physically stored on our servers on our cloud environment. For storage API, we have basically 3 types of storage. The most important is network storage, EFS storage. It's basically a file system that being mounted to all workers, and it contains 2 important things. Prover keys cache, that is being used by compiling and prover, and repos, because we dynamically import repos when the workers are running. The second type of the storage that we are being used is DynamoDB storage. It's being used for the keys. So when you run your zkApp in the cloud, you probably want to make sure that you have only 1 worker at time. You don't want to run like 2 or 3, so you can use key value store based on DynamoDB for it, or you can store some information, for example, job ID or proof or whatever. So it's second type of storage. And the third type of storage that is being used is S3 storage. It's mainly used as a temporary storage for deploying the repos. When you deploy the repo with command line interface tool, the process is as follows. The request is being sent to zkCloudWorker that generate some links, temporary links that will expire in 10 minutes. Then the command line interface tools upload using this link to S3 storage the zip file with repo, and then the zip file is being used and copied to AFS. We don't use S3 for prover case storage because it's slow. The AFS is much faster, so we finally decided to use it. We had code with S3, but it's slow, so S3 is just used for temporary repo storage, no more in this case.
Right, thanks. Thanks, DFCT and Mario. Any more questions? Seems not. Thank you again for the great presentation and your work. Looking forward to see more. Maybe last question from my side. Do you have plans to launch on mainnet, or like any schedule or any blockers? Yeah, what is your plan regarding mainnet?
For mainnet, it will be quite easy. What we will need to do is we will need to amend the library to support mainnet. It's quite easy, and we will need to add some workers because our experience shows that as soon as we share workers between the different blockchains, we have problems with stability for the reason that O1JS is using global variables, and then immediately we receive some problems with VAS. So basically, we have two steps to make mainnet available, and as soon as mainnet will be hard forked, we will be able to do it and provide this capability. We already tested it when we started zk support, and we invite everyone to test basically working with two blockchains that we support now, Mina DevNet and zkDevNet. There is some zk Boost program on the zk also, so probably you will get something interesting for testing it. And in this way, you can actually prepare your applications right now for the mainnet launch using zkCloudWorker. And as soon as it will be launched and we will have all the parameters, we need like a couple of days to deploy a new version and have the full mainnet support.
Amazing. Thanks again, and I'll stop the recording for your session.